Power Machines N5, Condensers, Module 4. Surface Condenser Example, Seawater Cooling. Earthly Teachings Channel. Don't forget to like and subscribe for more N5 tutorials. Let's read the question for this problem. Dry saturated steam is received by a surface condenser at a rate of 6,300 kilos per hour. The mercury manometer reading is 660 millimeters of mercury, while the barometer reading is 750 millimeters of mercury. The cooling water used is seawater. It enters at 20 degrees Celsius and leaves at 46 degrees Celsius. The condensate is undercooled by 4.7 degrees Celsius. The specific heat capacity of the cooling water is 3.85 kilojoules per kilogram per degree Celsius. The density of seawater is 1025 kilograms per cubic meter. We need to calculate four things: the absolute pressure in the condenser, the heat lost by the steam, the volume rate of the cooling water in liters per second, and the condenser efficiency. First, let's solve for the absolute pressure in the condenser. We are given the barometer reading, which represents the atmospheric pressure, as 750 millimeters of mercury, and the manometer vacuum reading, which represents the vacuum in the condenser relative to atmospheric pressure, as 660 millimeters of mercury. To find the absolute pressure in the condenser, we subtract the vacuum pressure from the atmospheric pressure. So we substitute our values. 750 minus 660 equals 90 millimeters of mercury. The question asks for the absolute pressure in the condenser, which is 90 mmHg. Now let's convert this to kilopascals. We use the conversion factor that 760 millimeters of mercury is equivalent to 101.325 kilopascals. So 90 times the ratio 101.325 over 760 gives us approximately 12 kilopascals. This is the absolute pressure inside the condenser. A quick look at the steam tables at 12 kPa shows that the corresponding saturation temperature is about 49.5 degrees Celsius. We will need this later. Next, let's calculate the heat lost by the steam in the condenser. First, we need the properties of the steam at the absolute pressure we just found, which is 12 kilopascals. From saturated steam tables at 12 kPa, the specific enthalpy of saturated liquid, or H sub F, is about 207 kilojoules per kilogram. And the specific enthalpy of vaporization, H sub Fg, is approximately 2,384 kilojoules per kilogram. The total enthalpy of saturated vapor H sub G is the sum of HF and HFG, which gives us about 2591 kilojoules per kilogram. Since the question states the steam is dry saturated, its specific enthalpy is equal to Hg. So the specific enthalpy of the incoming steam, H sub S, is 2591 kilojoules per kilogram. Now let's find the specific enthalpy of the condensate after it has cooled. The problem tells us the condensate is undercooled by 4.7 degrees Celsius. This means its final temperature, T sub C, is 4.7 degrees lower than the saturation temperature, T sub S. So 49.5 minus 4.7 gives us a condensate temperature of 44.8 degrees Celsius. This is the temperature at which the liquid leaves the condenser. To find the specific enthalpy of the condensate, H sub C, we need to look it up in the steam tables. We can approximate its enthalpy by finding the specific enthalpy of saturated water, HF, at the closest temperature in the tables. The closest saturation temperature to 44.8 is 45.8 degrees Celsius, where HF is approximately 192 kilojoules per kilogram. Therefore, we'll use 192 kilojoules per kilogram as the specific enthalpy of the condensate. Now we can calculate the total heat lost by the steam. First, the steam mass flow rate is given as 6,300 kilograms per hour. We need to convert this to kilograms per second by dividing by 3,600 seconds per hour. This gives us a mass flow rate of 1.75 kilograms per second. The heat lost per kilogram of steam, Q sub S, is the difference between its initial and final specific enthalpies. Subtracting 192 from 2591 gives 2399 kilojoules per kilogram. Finally, the total rate of heat lost by the steam, Q sub S, is the product of the mass flow rate and the heat lost per kilogram. So 1.75 times 2399 equals 4198.25 kilojoules per second. Rounding to significant figures, we get approximately 4,200 kilojoules per second, which is equivalent to 42 megawatts. This is the rate at which heat is removed from the steam. Now let's determine the volume rate of the cooling water required in liters per second. The fundamental principle here is that the heat lost by the steam is equal to the heat gained by the cooling water. The heat gained by the cooling water, Q sub W, is calculated using its mass flow rate, specific heat capacity, and temperature change. We know the specific heat capacity of the seawater is 3.85 kilojoules per kilogram degrees Celsius. The water enters at 20 degrees Celsius and leaves at 46 degrees Celsius. The temperature rise is the final temperature minus the initial temperature, which is 26 degrees Celsius. Rearranging our heat balance equation, the mass flow rate of the cooling water, m in .w, is the heat lost by the steam divided by the specific heat capacity times the temperature rise. Plugging in our values, we get approximately 41.9 kilograms per second. This is how much cooling water is flowing through the condenser each second. We have the mass flow rate, but the question asks for the volume rate in liters per second. So we need one more conversion. We'll use the density of seawater, which is given as 1025 kilograms per cubic meter. The volume flow rate, V.W, is the mass flow rate divided by the density. Dividing 40.9 kilograms per second by 10 to 25 kilograms per cubic meter gives us approximately 0.0409 cubic meters per second. Now, to get the answer in liters per second, we multiply by 1,000, since there are 1,000 liters in 1 cubic meter. This gives us a volume flow rate of about 40.9 liters per second. Rounding to a whole number, we get 41 liters per second. Finally, let's calculate the condenser efficiency. The efficiency of a surface condenser is defined by the actual temperature rise of the cooling water compared to the maximum possible temperature rise. The maximum possible temperature rise would be if the cooling water could reach the same temperature as the condensing steam. So, the formula is the outlet water temperature minus the inlet water temperature, divided by the saturation temperature of the steam minus the inlet water temperature. We have all these values. T2 is 46, T1 is 20, and T sub S is 49.5. The actual rise is 26 degrees, and the maximum possible rise is 29.5 degrees. The ratio is approximately 0.881. Multiplying by 100 to express it as a percentage, we get about 88.1%. Rounding to the nearest whole number gives us 88%. This means the condenser is 88% efficient at transferring heat. Let's quickly recap our answers for this condenser problem. We found the absolute pressure in the condenser to be approximately 12 kilopascals. The heat lost by the steam was about 4,200 kilojoules per second, or 4.2 megawatts. The required volume rate of cooling water was around 41 liters per second. And finally, the condenser efficiency was approximately 88%. Thank you for watching this example on surface condensers from the Earthly Teachings channel. Subscribe for more N5 tutorials.